It's nearly 5 past 5, and I have to say that for me it's a pleasure and an honor to be able to share this time with these women that are going to put you a bit closer to the space. These three women are going to tell us about their jobs in the ESA. I hope, in fact, I think all of you know what ESA is. The ESA stands, for European Space Agency. We are going to start this session with Pacros, who is going to tell us about how to build, to test, and to launch a satellite into the space. So I'm going to give the talk to Anne. We are going to leave the chat open for this intervention because Anne would like to interact with you a bit closer. Hope you enjoy what Anne has to tell us. So thank you very much, Anne, and wherever you want to.
Yes, good afternoon. I'm very, very happy to be with you today. It's great to see so many participants. I will try to speak slowly, and don't hesitate to tell me, Carmen, maybe tell me slow down, or if I go too quick. I will share a presentation with you now. Okay, it should be coming up in a moment.
Yep.
And yeah, Carmen, you can tell me if it's showing now. Yeah, okay, perfect. Super. So, as Carmen already said, I'm going to tell you about how to build and test a satellite. First, a little bit about myself. So, my name is Anne Pacros, and I'm an engineer by background. I have studied engineering. I'm from France originally, so I studied in France first. And after an engineering degree at the École Centrale de Paris, I specialized in aeronautics and space in the US. I went to the Massachusetts Institute of Technology for a Master of Science. And after that, I started working first in France, and then I joined ESA, the European Space Agency, in 2005. I've always worked since then on a science mission or science experiments. First, I was responsible for microgravity experiments. So this is science that you do in weightlessness. So it can be experiments in the space station, it can be experiments in a parabolic flight and things like that. After that, I worked on the science missions like ExoMars. This is a rover that will go to Mars. And more recently on Solar Orbiter, which is a mission to explore the sun. And what I'm going to talk about today, about how to design and build a satellite, this will be mostly based on my experience on Solar Orbiter, to really take this as an example. And I work on the Athena mission. Athena is a future mission that will look at it's like a telescope, basically, that will look at the universe in the X-ray aspects. My job at ESA is what we call a payload engineer. And more recently, I became payload manager. What does that mean? A payload for us means the science instruments. So when we have a mission like Solar Orbiter, like you will see, we have several scientific instruments because we want to study the sun. And so when you're a payload engineer, it means you're responsible for the development and the testing and the delivery of a scientific instrument. When I'm not at work, I also have a life. I'm married. I have one daughter who is 11 years old, so I enjoy spending time with my family. And in my free time, I also enjoy traveling, and I like to play music. I play music in a band. I play bass guitar, as you can see on the photo. All right, so that was me. And now let's dig right into the topic of the talk, which is how to design and build a satellite. But first, I have a question for you all. And that is simply, what is a satellite actually? So is it an object that goes to space or is in space? Is it B, an object that orbits the Earth, or is it C, an object in orbit around a celestial body? So that's where you can use the chat. Just put a letter in the chat. What do you think is the correct answer there? I'll give you a minute or so, and then maybe Carmen can tell me, because I can't see the chat, so what are the responses we're getting?
Bueno, chicas, no os
Okay.
veía yo tan tímidas. Hello.
What do you think is a satellite? Maybe I have a few pictures to start the discussion. So I think most of you will know that this picture is not a satellite. It goes in space, it's a rocket, but it's not a satellite. So that's not, so it's not A. It's not letter A. Now, if we continue, this second image, that is a satellite. You see, it's with these solar panels. It's floating in space around the Earth in this case. So yeah, that one is a satellite. But what about this one? Moon. Actually, the moon is also a satellite. It's also going around the Earth. What about this one? This is a satellite, obviously, but it's not around the Earth. It's around another planet. It's around Mars. So the correct answer is actually C. It's an object in orbit, meaning circling around another planet or another body in space. So the correct answer was
sorry.
C.
Sorry, Anne. I think
Yeah.
there was a mistake, and all of them right now, they have started saying that the correct answer was C. So all of them were right. Sorry.
Very good. Okay. No, it was no problem at all. It was a start. I have more questions coming. Okay. Next question is, what do we use satellites for? Maybe you're familiar with a few of those. So the first one is Earth observation. For example, to make the meteorological predictions, we use satellites like this one that take into space an instrument like a camera or radar and things like that, that allow to make very precise observations of the Earth. Another way we use satellites is for communication. For communication, meaning the telephone, also television signals can go via satellites. And for communication, you see the satellite has a different shape. It's not at all the same shape as the one for meteorological prediction. The communication satellite, it has these big dish antennas, these three white circles. These are antennas for the communication. So you see it's a different type of satellite. And one more type is for navigation. You know very well, in the car or on your phone, you have a GPS and you can have Google Maps and navigate. Well, that's also thanks to satellites. It's again a different type of satellites. As you can see, it comes in a constellation. We call that constellation because there are very many satellites. It's not just one. You use several satellites to know where the object, in this case a car, is located. But today I'm going to tell you about another type of satellite, which is to use satellites for research. And for research, the satellites are always different. It depends what you're going to study. We have, for example, telescope. We have exploration spacecrafts, like the rover that will go on the surface of Mars. It's very different types of machines that we have to build depending on what we want to observe. So now, as I said, I'm going to talk about the Solar Orbiter mission. And Solar Orbiter will study the sun. And this is a cartoon of how children usually draw the sun. In reality, it doesn't quite look like this. In reality, it looks more like this. And you can see in comparison a little white dot. I don't know if you see my mouse on the screen, but the white dot on the top right, this is the size of the Earth. So you see how big the sun is, especially with all the eruptions, these sort of eruptions of matter that are bigger than the Earth itself. So it's really huge. And so here comes another question, and I realize it might be a bit difficult for you to express in English, but what would you like to know about the sun? You know, you see the sun every day in the sky, especially in Spain. You have a lot more sun than us in the Netherlands. But what do you want to know? Tell me in the chat.
Okay. Don't know why this is always deactivated. Now it's activated, so you can go on and answer the question
Okay.
to one, please. Feel free. Well, they are not very much interested in the sun.
It's okay. I have plenty of questions I can give as an example. Yeah,
Okay,
we want to
okay.
know, is it
This is
fire?
starting to explode. The
Okay, tell
solar
me.
explosions. Solar explosion.
Okay, okay.
Okay. Oh
Mm-hmm.
my. This is what's inside of it. How can you
Mm-hmm.
explore it? Being as hot as
Yeah,
it is, how close can a satellite can get to the sun? Now, is it okay? The internal reactions. I would like
very
to know
good.
if it's going to explode one day. The degrees. How long do you estimate the sun will last? Maybe what's inside. What keeps the sun alive? Is possible to measure the temperature of the sun? How long will it last? Some of them are much
Very
more
good.
the same. So.
I hear some questions come several times, so that's very good because these are very interesting themes indeed. And I will be able to answer already a couple of them because even without sending a satellite to the sun, we can measure things already from here on Earth. So, for example, the temperature. I think somebody asked how hot it is and how can we measure it. So you can measure it from Earth, and actually it's one of the mysteries of the sun that we don't know yet how to explain, because the surface of the sun is very hot. It's about 6,000 degrees Celsius. But then if you look a little bit further away from the sun, you have what we call the corona. It's let's say a sort of environment around the sun, a bit further away from the surface. And this so-called corona, it's more than 1 million degrees Celsius. So that's a bit strange, because if you go away from a hot object, you think, okay, if I go away, then it will be colder. But in this case, not. In this case, the surface is a lot colder than the corona. So that's a mystery we want to know about. Another mystery of the sun, oops, sorry, I clicked too quick. Another mystery of the sun is it linked to how it works inside. So it's very important to know that the sun, it's hot, it's not fire. It's called plasma. It's basically some nuclear reactions that happen inside the sun, and it's a hot ball of gas. It's a sphere full of gas and plasma, and this ball of plasma, it changes. It's not always the same. And there is a cycle. So every 11 years, it becomes more active. It shows at the surface some dark spots, a lot of activity with these eruptions, and then it calms down. And then 11 years later, it starts again. And this is another mystery of the sun. We don't really know why it has this 11-year cycle. So we're going to build a solar orbiter to go and try to answer these questions and these mysteries about the sun. So this is a drawing of solar orbiter, and to explain to you what we need to build a satellite. So because we're going close to the sun, we're going to need a heat shield. This is this black part on the front side here of the picture. It's protecting the satellite from the heat of the sun. Of course, you need also a strong structure to carry everything on the satellite, the instruments in particular, the scientific instruments. You need the solar panels on each side. You see the long solar panels that will give the electricity that the satellite needs to function. It also has a communication antenna because, of course, you want to be able to send a command to the spacecraft and you want to receive the data from the spacecraft, from the instruments. And maybe something you wouldn't think about, but you also need to have the so-called isolation blankets against the cold, because it's going to get very hot at the front of solar orbiter, but it's going to be very cold at the back, because the back of solar orbiter is facing deep space, and in space it's very cold. So we also need to design against the cold. This is another drawing where I wanted to show you how complicated it is inside the satellite. So it's a view from the other side compared to before. And you see inside the satellite itself, you have several types of cameras. Some cameras look into infrared, some look into X-ray, some look into UV, different types of wavelength of light. And they look through small windows in the heat shield. And then you have other types of instruments that are more outside of the structure of the spacecraft. Like, for example, on this boom, there's a long boom at the back with, for example, the SWA, MAG, RPW instruments. These ones are measuring the particles and the solar wind, the particles that the sun sends away from it. And these instruments are specialized in that. They can measure the particles from the sun. And now I'm going to show you the picture. And it's really nice when you've worked on a project like this, you've done all the drawings, you've done all the design, and then one day you have the satellite finally built, and this is what it looks like. So you see, if I go back to the previous slide, it looks quite like the drawing. You see very well the heat shield, the different openings in the heat shield over here in the front. Only the solar panels are not deployed here. The solar panels are folded because that's the way the satellite is prepared to fit in the rocket. The solar panels are deployed later. So it's very nice to see that we have built solar orbiter like this. But now, before we send it into space, we have to prepare it. We have to test it. And there I have a couple of slides to explain to you that space is a strange place. And my question is, you know already, why? Why is space a strange place? What is different in space compared to on the Earth? Can you tell me a couple of words in the chat? What can you think about? What is different in space?
Gravity? Gravity?
Gravity.
There's no gravity? Vacuum?
Yes, indeed. Gravity, there is actually gravity everywhere, but I understand where you're coming from. You're saying if you're orbiting the Earth, for example, in the space station, indeed the astronauts, they are floating around. It's not that there is no gravity, it is that's what we call the microgravity environment. You're circling around the Earth and that makes you float in the cabin of the space station. But there is gravity. But indeed, so where we have already vacuum, that's very good. We're going to have to test that our satellite can survive in vacuum. What else?
You have composition, temperatures, not limits, radiation level. Wow, I didn't know that there was something like this. You correct me.
It's very good.
She asked. Well, she says about Bok holes. Is there any kind of similar?
Yes.
Regarding. Yes. Okay, but I'm learning something new, girls. Thank you.
Good. You have indeed, I think, everything that I have on the slide has been quoted at least once. So indeed, in space you have vacuum. In space you have hot and cold temperatures. It's a bit like when you are, it's a cold night and you want to warm up in front of a fire, in front of the chimney, and you put your hands next to the chimney, so your hands get warm, but your back stays away from the chimney. It still is cold. So in space you have both. You have hot and cold. You have to manage that. Your satellite has to survive hot and cold temperatures. And I think somebody also mentioned radiation. Radiation means it's this electromagnetic radiation and the particles that I mentioned that are coming from the sun and from the rest of the universe that can damage your electronics in particular. So this is all very good. So we know space is a strange place.
We have more, and we have other contributions such as the sound, the cold, the silence. There's no substance. It's empty. It is in continuous expansion. It makes it harder to study. The pressure.
Very good. So the pressure and the vacuum, the fact that it's empty, it's all what I called under the vacuum. But I heard a very interesting word, which takes me to the next slide, because somebody mentioned vibration, I think, and that brings me to the launch. So of course, to get your satellite into space, you need to put it in the rocket, and the rocket launch is a quite dangerous moment for the satellite. I have a small video. I hope it works. Let's see. Whoop. Coming back. It doesn't want to work with me today. Interesting. So anyway, it's a video of a rocket launch, and maybe some of you have seen one. So when the rocket goes up, you have all the engines of the rocket that lit up together, and it makes a terrible noise and terrible vibration. And so the satellite at the top of the rocket is being shaken and has to withstand this vibration and this large noise. So all in all, the launch plus the space environment, it means we have to test our satellite with a lot of tests. So I have here some pictures of Solar Orbiter being tested. On the left side, you see it for the vibration testing. The vibration tests we do on a kind of platform like you see here on the left picture. It's called a shaker. And that's exactly what we do. We put the satellite there and we shake it at different frequencies, different intensities. And we make sure that nothing gets loose, nothing gets broken, to make sure that the satellite will, in the end, survive when it's in the rocket. The picture on the right shows what we call the acoustic tests. That's about the noise. Acoustic test means you use very big loudspeakers. It's the white circles you see on the right side of the picture. And you put a lot of noise onto the satellite. And what noise is, it's basically a vibration of the air. And you make sure that your satellite doesn't break up from this sound, from this vibration. So these are what we call the mechanical tests. And then for the aspects of the space environment, we talked about hot and cold, we talked about the vacuum. We use what we call the thermal vacuum test. We put the satellite in a big chamber. That's what you see on the picture. You see Solar Orbiter in the thermal vacuum chamber. And this chamber, we pump it down, so it's vacuum inside. We close the door, of course, and then we pump it down. It's in vacuum. And then the black panels on the right side, all around actually the chamber, we will cool them down to really cold temperatures. And that will represent the cold space. And then at the back side of the chamber, we have like a big lamp. And this big lamp will simulate the sun and will heat up one side of the satellite. And there we can check if the satellite survives this difference in temperature, being very hot on one side, very cold on the other side. And we can also make cycles. We can say, okay, maybe the temperature is first hot, then cold, then hot again. Variation in temperature, we also check that the satellite can survive. And actually, we check that not only it survives, but also that it can operate. We want to make sure that each instrument can be switched on, can take science data, while being hot on one side, cold on the other side. Apart from that, there are many, many more tests. For example, deployment tests. You saw the antennas, you saw some the boom at the back of the satellites. All of that has to be deployed. That means mechanisms have to be activated, so we test that. We also have the so-called electromagnetic test. This is to test that there is no interference between different systems on the satellite, between the antennas, for example. They shouldn't interfere with each other. And we have the functional test. Functional test means we switch on everything, switch on all the instruments. We have 10 instruments on Solar Orbiter, so we have to switch them on all in turn and make sure they all work properly. And so after you've done all these tests, your satellite is ready, and now you're going to put it on the rocket. So at one side of the satellite, you have this kind of ring. And this ring is what is being used to attach the satellite to the rocket. And this is what it looks like. So this is in the launch center on Cape Canaveral in Florida, because this is where Solar Orbiter was launched. So you see our little Solar Orbiter here, all black, with its attachment ring, and you see the two parts on left and right. These are called the fairing. So you basically bring them together around Solar Orbiter, and you encapsulate the satellite in the fairing. When this is done, it looks like this on the left picture. Solar Orbiter is in there, in that white box, that white thing, that's the fairing. And just behind it is the rocket, the very tall rocket. And you're going to, with the crane, you're going to lift it up and put the fairing at the top. And you see here on the right side two colleagues from the US putting the fairing on top of the rocket. It's a very delicate operation, of course. And yeah, Solar Orbiter is inside there. So that's a very exciting moment, of course. You've tested your satellite, you hope everything is fine, and then finally the satellite is launched. So that concludes basically the development work, but it doesn't conclude the mission. On the contrary, it's only the beginning of the mission. So what happens after the launch? In the case of Solar Orbiter, it was launched about 2 years ago, 10 of February 2020. I've put here, and of course you can have the slides after this presentation, so you can go have a look on YouTube, you can watch the launch, the actual launch orbiter. And once the satellite is separated from the rocket in space, several things still need to happen. Let's see if this video works. Well, maybe not. It's not my day today. Anyway, after the satellite is separated from the rocket, the very first thing you want is that you have communication with the satellite. So you have what we call acquisition of signal. It's the first time that the antenna of the satellite is communicating with the antenna on the ground and telling you, yeah, the satellite is healthy, everything is going well. You can start doing the rest. And the rest being you deploy the solar panel to make sure you have electricity on board. And then you deploy all the rest, the antennas, the instrument, boom. And after that, well, that's the beginning of the long journey in the solar system to get to the orbit around the sun. And for this, you have a very interesting website here, which you can go have a look on afterwards. It's a tracker. Basically, it shows you where is Solar Orbiter now. It can tell you, it can trace actually from the launch until today, where is Solar Orbiter. And actually, it's approaching, right now, it's approaching closest approach to the sun. So it's pretty interesting times for the scientists. We've already received some images from Solar Orbiter, and this will be my last slide. You can see on the left different images from the different instruments on our Solar Orbiter. And so that was really a great achievement to see after so many years of developing and testing the satellite. You see actually that all the instruments are working perfectly and it's taking those beautiful pictures. On the left, you have different wavelengths, different pictures from the UV instrument or from the visible light instrument. And on the right side, you have a very typical image for solar science, which is called from a coronagraph. A coronagraph is basically an instrument that allows to make an image of the corona, the part that's around the sun. It blocks that's why it's black at the center. It blocks the light of the sun. And you see the corona around it. So those were very gratifying moments to see our instruments working so beautifully and taking such beautiful pictures. So that's all I had to tell you today. You're very welcome to ask me any questions now about either what I do, what I studied, or about the information in this presentation about how to build and test a satellite. Thank you very much. Stop sharing, so hopefully you can see the video again, and I'll have a look at the chat now. I think there were a couple of questions about when will, if the sun will explode, when it will finish its life, or how long the life is. I think the life of the sun is, we're now at about half of its life. So we will still have another few billion years until the sun dies. But when it dies, it will not be like one day a big giant explosion. It will also be a long process. So no fear about the sun exploding in our lifetime.
That was great. Good to know.
Yeah,
We have plenty of time then. Siham was
exactly.
asking that what has been the most important information you have acquired from this mission?
So the mission is it was launched years ago, but it takes time to get to the final orbit. So actually, the actual measurements of the sun that we are making have only started last month. The images I showed you, they were like just to try that the instruments are working. So the science is actually starting only now. So I can tell you already one thing that was discovered is thanks to the very precise cameras we have on board. Some of the scientists have discovered that at the surface of the sun, it looks very inhomogeneous, and in some places you have what they called campfires. So it's not really a campfire, of course, but it's some bright spots, and they think these bright spots are what generates this very high temperature in the corona, because they're very tiny, so we couldn't see them before. We could only see them with our very precise cameras on Solar Orbiter. And these little spots at the surface of the sun being so bright, they release a lot of energy. And they think it's this energy that heats up the corona. And that's why the corona might be hotter than the surface of the sun.
Okay, so let's go on with the next one. I was just having a small chat with my mate, because as this masterclass is made by Joan, by Elisabetta, by Lydia, I think you have a short spare time, and maybe if you agree, girls, we are going to take maybe a couple of or 3 questions more and leave Elisabetta to go on with the master class, because, well,
for sure, yes.
We know that the girls can be questioning you until 8 o'clock, I'm sure. But
I'm sure. I see now the chat, and I see also some questions, not so much on Solar Orbiter, but also on what I studied. Did I always know? For example, one question I see here is, did I always know what I wanted to study? In my case, no, not always. When I was maybe 12 or until 15, I wanted to do different things. I wanted at some point to be an architect, to be a race driver, like a Formula One driver, that sort of stuff. So I was not at all into space. And then one day I was reading a magazine about astronauts and about space, and that's what caught my attention. I was like, well, that looks really cool. And I wanted to be an astronaut. And I studied for engineering because I liked it, and also because I had in mind, oh, maybe if I'm an engineer, then I can become an astronaut. And I didn't turn out to be an astronaut, but I really loved the engineering aspects. And so I went into space engineering. So it's not like you need to have a dream from when you're very young. It all comes one thing after the other. You get influenced by something you've read or by somebody you've met. And then it helps you decide what to study. And then once you start work, it's not a one straight line. You go from opportunity to opportunity. So when I started at ESA on the microgravity experiments, this has nothing to do with Solar Orbiter, but still, I could work on Solar Orbiter at some point. So there are many opportunities, and you have to just be open for opportunities. Another question along the same lines is if anybody in my family guided me. Actually, no, not really. My family is, my parents are teachers, were teachers, they are retired now. So, but not at all in science. They are teachers of English and history. So I'm kind of the first science person in the family. And that was fine. I got guidance not from my parents or my family, but more from people at school, from the subject I loved. I loved math and physics, so I was lucky to have good guidance from the teachers at school.
Okay, so I think all the girls are much more giving you thanks. So thank you
That's
very
great.
much, Anne.
I have my email address on the front page of the presentation. I'm always very happy to answer more questions later. If people want to email me, that's absolutely no problem. So don't hesitate.
You
to
don't
do
know
that.
what you have just done, Anne. Oh my. Anyway, thank you very much, and I leave you introduce Elisabetta because I think
Yes,
you know better.
absolutely. Yeah.
Yep.
No, indeed. So I will pass the floor now to Elisabetta. She has been working at ESA for a little over 10 years. She's in what we call the cost engineering. So I will not explain what cost engineering is because I'm sure she will do that much better than me. But so you will see what we have in ESA called cost engineering. And from her background, she's also actually an engineer by background. She studied in Italy. She's Italian, and she studied space systems engineering in Italy and in also other places. So for more details, I'm sure she will tell you in her presentation.
Good.
Over to you, Elisabetta.
Thank you, Anne. Thank you very much for your presentation. So let me share my presentation as well. Let me know when you see that, okay? Do you see my presentation?
No, so far. Give it another try.
Let's try it now.
Now.
Yeah.
Now you have it. Yep.
Yes. So basically, this is me, Elisabetta Lamboglia. As Anne introduced me, I'm a systems and cost engineer. I recently joined also the Climate Change and Sustainability Office as direct support to the strategy of the Director General Service in ESA. This slide, trust me, is not to bother you about me and my background and who I am. It's just to tell you, girls, I feel so honored to be here because you are the next generation. You are the future generation of girls, of women, of professionals, of leaders. So this is the key point. Yes, you can do it always. So as far as you believe in yourself, you can do it. You have all the details in this slide concerning me, my, let's say, the background, education, where did I study, not only in Italy, the database where I belong to, it's an Italian database for STEM, the articles that have been written on me, and my email for the Mentora Star and Girl system. So feel free to reach me if you have any question, if you want to ask me a question. So my formal job title is cost engineer. What does it mean? And this presentation is on programmatics. What is programmatics? Programmatics is really an ensemble of design systems. Yes?
Sorry, we are just watching the first slide, and I think you're watching the slides go by. So maybe if you put it into presentation mode, maybe.
You prefer not to have it in presentation mode? Can you see that now?
Now, yes, but before it was like the guide of the slides. So once you started talking about the next topic, we couldn't see the information. We
Can
just
you see,
remain
let's
at the
say,
very beginning.
my picture? Can you see my picture?
Now, yes.
Okay, that's good. This is what I wanted to say before. You have all the details in this presentation. In case you want to share it, feel free to contact me. You have also at the bottom line also my contact for the Mentora Starling Girl email. So for anything you may need, feel free. So I'm moving to the third slide. Let me know if you see that.
Yep.
What is programmatics? Programmatics is really an ensemble of information and important information about space mission concerning the design, the development, the cost, the management, the risk, the strategy, the planning. So it's not only technical information, but is the technical information joining, let's say, also financial and budgeting outcomes. And this is really fundamental. This is why I'm a cost. I am also an engineer. It means that based on technical information, I need to evaluate very often the credibility of this mission. It could be a launcher, it could be a mission orbiting Earth, like in Earth observation, it could be a science mission, like the one that Anne has been presenting before. So it's, let's say, it's very, very complete discipline. You have in this slide all the links to the ESA website, the official links, so feel free to consult them. While Anne has been presenting, let's say, the assembly and let's say really the development, the physical development of a spacecraft before, my discipline, cost estimating, it's something that really happens at the very early and very beginning of a life cycle of a space mission. I call it life cycle because it goes in phases. We call it in, let's say, in system engineering, we call it phase A, phase B, phase CD, and so on. And depending from where you are, there are different methodologies to estimate the price and the budget of a space mission. And this is really important in order to understand if technically it is feasible, but also it is compliant with some cost requirements, if you can really make it, because something can be very attractive technically, but maybe it's really impossible to develop within certain budget available. So this is not to annoy you, but this is just to tell you that there are several ways of estimating depending on the difficulty and depending on the stage. Can be a rule of thumb, like I think that this equipment might cost X, more or less, yes, it's okay. Or as an analogy, it could cost X because it's very similar to the other equipment. So I think they're very similar. There is an analogy. I think more or less we are in that range. And then so on and so on, depending on the complexity of the target, of the scope. And I personally been developing models. They're very analytically based. They're very much based on data, on data gathering, on analysis. So let's say there is an entire work behind that, but yes, there is a team associated to it, so we usually do it. And these models can be very simple, but can also be very, very complex. It requires years to be developed. This is just an example, but just to give you an example, very often models, normally at very beginning of a life cycle, can be, let's say, quite simple. So not all the methods can be applicable, but in some specific cases, like for example, in the Gaianeer, it was a study that it was totally based on another mission that was Gaia. So externally, you could not make the distinction between the two spacecraft, totally identical. One was real, the other was a design, in a design phase. So in principle, that really I could really apply both, but also more than both, 3 or 4 different methodologies to estimate their costs. These models are named cost estimating relationship. They can be linear, power. There are many. You will find this information. You cannot even Google it. It's very, very, let's say, now common to have this information. It's all about statistics. It's all about regression and curves. It's very mathematical approach to it. But at the end, what really is fascinating is to understand what could be the overall programmatic envelope. So if you could make it in terms of cost again, of risk, on planning, of a mission to be. And this mission, you see in the picture is composed, for example, by a spacecraft that has to fly to orbit the Earth, our planet Earth. I will show you some example later on. And then go into the details on different components and equipment for this mission or for this spacecraft, trying to understand if you can make it for all the different layers and to the different, for example, for the solar arrays, for the propulsion, or for the antennas, or any other payload. This was an example to tell you that models can be also quite complicated based on different, let's say, consideration. And this consideration can be also given by external factors. Factors like the market. So competition, for example. So price or programmatic envelope is not only based on pure objective and mathematical factors, like, for example, how big is your spacecraft, how much is weighting, and how complex it is. But complexity can also be given by factors given by, for example, the role of a certain industry that has to develop that, or the competition scenarios, or also the periods. The period can affect the price a lot. Let's just imagine, for example, just the pandemic and what has been creating all around the world, and this is affecting also, of course, the space market, as all the other markets. The models can be also very, let's say, multivariate models. It means that they're not based only on one factor driving the price, but they could be based on different factors, like, for example, the technology. Let's talk about the risk. So more than the risk, I would like to just have a word on the contingencies. So what is important to do is to just split what is the estimated cost from the contingency. And the contingency is an additional price that you keep as a reserve. You know, when you say, I like that dress, it's going to cost 100, but I see it, it's very, I don't know, it looks very nice, could also cost 120. So maybe if I keep 120, probably I will make it better. I will keep it. I will take it. Okay, because 100 maybe is not enough. So this is a little bit what we do in the cost estimating role, including contingencies. And what is important, however, is to keep the contingency always separate from the original nominal price. Why? Because anytime you estimate a price for a certain product, if you don't split the red part from the blue part, you start from a previous, let's say, example or analogy that it's already including a margin. It means that anytime you will, the price will grow and will grow and will grow, which is not good. So at the end, the lesson learned is that it's important to split what are the real price of a certain equipment from, let's say, the green part from the red part, to understand what you can afford and what you could still add on top, but separate. And programmatics means also planning, and planning is not marginal. Actually, somebody, when I was working for the oil and gas industry in the Netherlands, told me that the planning and the schedule is the most important document. It's a live document. It means that it varies every day on the daily basis. If you take a schedule of a mission today, compare it with the one of 1 week ago, most probably it's changing, because there are differences in terms of developments, criticalities, changing things and evolution that might affect the schedule. And the schedule is also affecting the people working on that, and is also affecting the price working on that, and is also affecting at the end the feasibility, if you want, of a certain mission. So there are models that also try to simulate from very early stages what could be the planning, the design, and the development of a certain, let's say, spacecraft. So these models are based on certain, let's say, drivers. I'm not here to go into the details to the drivers, but to let you know that it's important to do that from the very beginning, because this is also part of programmatics. Here you have an outcome, it's an example, and you have the duration of a planning. It could be like very, very simple. and concise like the one on the upper part, or like more precise, going to the definition of each one of the instruments, because one spacecraft can contain many instruments, as the one on the other side of the slide. Here with this slide, we thought about Anne has been presenting a science mission solo. Here I just make an introduction, just mentioning many let's say Earth observation missions. So looking at the Earth, orbiting Earth. With EE, it stands for Earth Explorer. We had 7. I've been working on them since year 2010. And then you have many of them, and let's say with this programmatic evaluation, it's important to, let's say, work on different aspects, not only in the reviews, not only in the procurement phases, but also in consultation. For example, I've been asked to work for Agenzia Spaziale Italiana. I'm Italian, for some criticalities. So it's a very complete approach to feasibility of a space mission. And then maybe you heard about these 6 new missions. They are very, I'm not going to the details. For these 6 missions represent the Copernicus Expansion. It's a mission, it's an envelope, it's a program that is partially funded by the European Commission. And it's a European Commission program. What happened is that ESA had to start the procurement and sign the contracts and ask industry to start working on those 6 missions in parallel during pandemic. So all the massive job has been done in parallel for 6 missions altogether. But I can tell you, ESA-wide, we've been working so hard to make this happen, because we didn't want to stop, let's say, working on the environmental security of Europe and to grant it for probably the next 20, 30 years. This is a very ambitious program, and it's recognized worldwide. So very challenging, very attractive, very fascinating, I would say. Okay, just to make it in a nutshell. So my role as cost engineer, it's always in between, you know, several other disciplines. In terms of financial data exploitation, so how to check the quality of the data, is very analytic. It's also in between, let's say, the design definition, the work breakdown structure of the overall, let's say, the product tree. The overall product is a spacecraft, or it's a launcher. So understanding the pieces, the parts, their complexity. Is everything inside there? Are we missing something? Is there any criticality? So it gives you a system level overview. And there is a direct interaction with project controllers, which is other, let's say, characters. And they're really working only on financial information. Then, for example, to estimate and to understand if there are similar analogies, which is not always the case, because in the space business, all let's say, products are very innovative. So it's very rare to have something copy and paste from something that has been developed just recently. So it's important to understand if there are analogies. And here I'm also asked, and I'm happy to face other disciplines and to compare and to work with them. And also another important point is, let's say, the evaluation of the manpower. What is the manpower? How many people do we need to work on specific tasks to develop a spacecraft or a fleet of spacecrafts? So I think I've been quite fast. I think I managed to be fast enough today. Here you have the bibliography in case you're interested to that. If there are specific aspects you want to investigate more, again, please contact me, no worries. And in case you have any question, I'm here. Maybe we can just keep the next few minutes for that.
Okay. Well, girls, I'm going to open the chat so you can ask the questions you may have. Please go ahead through the chat and feel free to ask Elisabetta whatever thing you are questioning about.
I see that the same question has been asked to Anne, and I wanted to answer. I really wanted to answer that question, so I'm going to do it now. Do you think it's hard to get in where you are now? Well, let's say I would never thought I don't know, I could be, let's say, an engineer of the European Space Agency. But once you understand what you like really a lot, there's nothing you can do. I mean, you can do anything. Nothing is impossible. I mean, very rarely. So yes, it's hard, but I think it also depends, because if you like studying, I don't know, philosophy, for example, and then you're forced to study aerospace engineering, then it's really hard. But if you like the topic, then it's not hard. It's fine. You do it because you're stimulated. So yeah.
Any more questions to Elisabetta, girls? I think you left everything so clear that they have. But anyway, you just left your email contact.
Yeah, everything is in there.
And you offered yourself to answer them any question they may have. I repeat the same as Anne. You don't know what you have just done, but well, hopefully it will be fine. So
Okay.
if you want, we can go on with Lydia, and maybe
Yes.
if they have any question at the very end, they can always ask them to you. Don't you think? Yeah.
Yeah. Yeah. Okay, I'm happy, and I actually am very proud to introduce you Lydia Cardi. She's 38 years old. She's from Italy as well, and she's graduated in electronic engineering. She first worked in Italy, in Thales, Alenia, in Thales, Italy, on Baby Colombo, which is a science mission. It's an ESA mission, and then she joined ESA in 2011, and she joined before Solar Orbiter, SOLO, so the same mission that Anne introduced you before. And now she's working for another mission, which is named Ariel, as an avionic engineer. So happy to share this with you. I leave you to Lydia.
Thank you, Elisabetta. I hope that you can hear me. Can you hear me well?
Yes, yes, we can hear.
Thank you. So, buenas tardes, chicas. Estoy muy feliz de hablar con vosotros aquí. Pero voy a hacerlo en inglés porque mi español no es suficiente para eso. So I am going to share my presentation with you in a moment. Please tell me when you see it.
Is there?
Perfect.
Yep.
So we start. So today I thought I would tell you a bit about how it is that I ended up working at ESA, which challenges I had to face to get there, and how it is for me to work as an engineer at ESA, and also which challenges I am facing right now in my job. And then in the end, I will also tell you a little bit about the fact that I am an expat, so I am working abroad, and what it means, and how it is to work outside of your home country, because I think that it's an experience that many of you will probably have in the future, so it's maybe interesting for you. So we start a bit with my education and background. So in Italy, we do the secondary school, which is from 14 years old to 19. And in my case, this was called Liceo Classico. It is a kind of school where your main focus is language and literature. You study Latin, you study Greek. It's a humanistic school. You study history and philosophy. You have little hours to do math, chemistry, or science. It's not really the focus of the school. But then, when I had to choose which university to attend, I kind of completely changed my course, and I decided to go study electronics engineering at Politecnico di Torino. Politecnico is quite good engineering university in the north of Italy. So this is what I did for the university, and of course the focus is, of course, electronics. So I studied a lot of math, geometry, physics, chemistry, computer programming, and also a bit of English, which was then very useful later on. And what I would like to tell you about this, and what I would like to show you, is I found it very interesting, because I was trying to find statistics from when I started studying, but I am too old, so there are no statistics, or I couldn't find any statistics for those years. So I found some numbers for the year 2019, and this is the difference between girls and boys that start the secondary school. And you see here, the first one is Liceo Classico, which is what I did, still overwhelmingly done by females, by women. While if you see, for example, here is the technical technological, it means the more technical studies, lots of boys. And the same statistics is for the university. Here you see yellow is women and blue is men. And if you go and check engineering, it's still very unbalanced. And this is from 2019. So I found it very interesting. Of course, it's not bad or good to study engineering or philosophy or literature, but still the imbalance between men and women is still very big. And also, of course, when you are 14 years old, it's a bit difficult to decide what you want to be in life, and maybe you tend to go with the flow, with the mass, with the majority. Luckily for me, it was kind of not so difficult to change and to study engineering. Yes, you have to make up a bit of what you didn't know, but it was not so difficult. It's feasible. Lots of women do it, and with no issues, which is nice. Then what happened is that I finished university, and then I started working in industry. So starting in the outer world, let's say. How did it happen? So at the university, my thesis was called Modular Power Subsystem for Nanosatellite Aramis. So the nanosatellite, here you have a picture which is an example. It's not Aramis, which is the satellite that my study team was building at the time, but it never saw the light of day because it was abandoned at some point. But it was anyway a satellite similar to a CubeSat, of which you can see an example here. CubeSats are small, kind of simplified satellites that at the time were built mainly by universities, by students, in order to learn how to how you build a spacecraft. It was a great way to make some experience. Nowadays, they're also built by some industries. It's a bit changed, but anyway, they are kind of tiny, a couple of kilos in mass, and they produce a couple of watts in power. And my job was to design the power tile. We call tile one of those, the faces of this cube. So one of those faces had 2 solar cells and a bit of electronics, so it was able to see the sun, produce power, and distribute the power to the whole spacecraft. So this is, well, to the whole satellite, not really a spacecraft. So this is what I did in my thesis when I graduated, and then also a few months later on. And thanks to this experience, I was then able to find my first job outside of the university, which was in Thales Alenia Space in Torino. Torino is where I was living at the time. Thales Alenia Space is a company which builds, among many other things, spacecrafts. And I was hired as a power engineer. So I was working on a spacecraft named Bepi Colombo, which is a scientific spacecraft. Anne has explained very well before that there are many kinds of spacecraft, and I have always worked so far on scientific spacecraft, so spacecraft that study the outer space. And this was a mission to the planet Mercury, very interesting. And you can see the difference in, let's say, in size that I had to face. So while my previous work was a couple of kilos, here we are at 2,700 kilos and 2000 watts compared to the couple of the 2 watts that I had before. So the challenge was certainly technical. I was responsible for the procurement of the solar arrays. Procurement means you follow up the companies that do the design, that build the solar arrays, that make the test, and then they deliver it to your company. Each of these solar array wings, we call them wings, included thousands of cells, similar to the ones that I was using before. So while before I had a couple of cells, now I was in the range of thousands. The technical challenges were many. This spacecraft was near to the sun, so there was high temperature, sun illumination and radiation. There was the mercury albedo, very interesting. So the sun, that the light and radiation was reflected on the planet Mercury and then reflected back on the rear side of the solar array and was making them very hot. So it was a big problem. But also the challenges that I had to face were an international environment. So suddenly I was working in English with people that were with different companies that were in Germany, in France, in Spain, in different places. And also I was very young. I was 26. It's not easy to be a young girl and to have to work in an environment which is full of much older men. So you have to work on yourself, on your assertiveness. You have to work on your facts. You have to get your information right. You have to be knowledgeable, and also you need to expose your knowledge in a certain way so that you are listened to, so that you are respected, and you can work with these persons. It's a very interesting challenge that I had to face. Then what happened? I applied to a position in ESTEC, well, in ESA. ESTEC is the part of ESA where I work. The position was the job was power subsystem engineer for solar orbiter, and you know already this spacecraft because Anne has described it to you so well. I am not going to repeat it because now you know everything about it. But I want to explain very briefly this. What does a power subsystem engineer do? So if before I was caring, let's say, for the solar arrays, now I had the whole power subsystem to look after, which is composed by the solar arrays, the SADA, which is a small motor with some electronics that is going to turn the solar arrays towards the sun or away from the sun, according to the needs. The PCDU, which is an electronic box which takes the power produced by the solar arrays and distributes it in a safe way to the whole spacecraft. The battery that gets charged when the solar arrays are producing more power than needed, and then you can use the battery to power your spacecraft when there is some shadow and the solar arrays are not working. The harness, which are all the wires and cables that connect the whole thing. So this spacecraft, let's say it's the same order of magnitude as Bepi Colombo. So you can see here the weight and the power, more or less I was in the same, let's say, in the same league. And also the technical challenges were quite similar in some sense. It was going near to the sun, so you have the temperature and so on. What changed from my previous job? My role changed, because before I was working for industry and now I was working for ESA. So industry builds and tests spacecrafts or parts of spacecrafts and then delivers them to ESA, which is the final client. So I had to change my mindset, because now I was the client instead of the contractor. What does the client do? We enforce the schedule so that everything is produced, but also on time, not only correct, but also on time. We have the specifications, so we tell the industry we need this, 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 and that, and this needs to be fulfilled. And we have standards, so we have some best practices that industry needs to apply in order to do a design that is correct, that is robust, and that resists all the stresses. I had to review the design and documentation of the industry, and I had to accept or reject the technical solutions that they proposed. Another thing changed for me. So I was taking care of the solar array, and now I had the whole power subsystem to look after. So I needed a higher level system vision, because I had less time to go into the itty-bitty details of everything. And I had to choose priorities. What do I follow? What is the most important thing? What can I leave a bit behind? And also I had to expand my knowledge and expertise, because before I was only looking at the solar arrays. Now I needed to know a lot more things. And this is also a very interesting thing, because it almost never happens that you work only on something that you have studied at the university. In reality, you go on learning and learning and learning more things while you proceed with your work. Also, another thing that changed, the international environment. Yes, I was working in English before, but now I was in ESTEC, so I was speaking English at work, but also during breaks, with the friends, with the colleagues, with everyone. And I tell you, it was at the beginning very complicated. I still remember some days, starting my day in the morning, I hadn't talked to anyone, and then I had to talk in English to someone, and I felt like I had a potato in my mouth and I couldn't speak. It was really an obstacle at the beginning. Then you get used to it. Different cultures and styles of communication. So we are from different parts of Europe or the world. We need to be mindful of the fact that someone is more direct, someone is more introverted. We need to be careful with the communication. And also I traveled quite a lot, but of course this was previous to the pandemic happening. So this was solar orbiter. Then in 2019, as Anne has told you, the solar orbiter was launched. It was a fantastic experience, but then of course I had to find another position. So what I started to do after solar orbiter is Ariel. Ariel, so the job is called Avionics System Engineer, but the mission is called Ariel, and it's a mission which studies exoplanets. Exoplanets are the planets that are not in the solar system, so that are outside the solar system. And it is estimated that there are 10 at the power of 12, so 1 with 12 zeros after the 1. Of course, we are not going to study all of them, but we have questions. So what are those planets made of? How do they form? And the planets and their atmospheres, how do they evolve in time? So this spacecraft, which we are now designing, is going to observe hundreds of planets, different sizes, different temperatures, and different type of stars that they orbit around, and we'll kind of categorize them to see if we can find some similarity between them, and find a way to categorize them. Avionics system engineer is my role now. What is an avionics system? Well, in this case, it means the power subsystem, which is the one that I described before, and in addition, the communication subsystem, which are the antennas, the transponder, everything that is necessary to receive commands from ground and to send telemetry, which is like the status of the spacecraft, and also all the scientific data from the observation of the planets to ground. Data handling is the onboard computer, which is the intelligence of the spacecraft, and also the memories. So the memory, especially the mass memory, is the one where you register, where the spacecraft registers all the data, all the observation data of the planets before being able to send them to ground. Harness, as we said before, and also electromagnetic compatibility, which means making sure that all the atoms in the spacecraft, they don't disturb each other with the emission of radiations, or basically with the emission, the electrical and magnetic emissions. So this is what I have to do now. Challenges. Of course, the number of topics has increased exponentially, as you can see, so I need to learn a lot of new things. I need to read, study, I follow trainings that are luckily provided by ESA, and also I ask a lot of questions to the experts that know a lot more than I do. In fact, I have the support of technical experts, so it's people that are really very expert in a specific field, and they support me in that field. And apart from asking them a lot of questions and learning from them, I also need some skills of people management, which means I need to build a relationship with these people, a stable relationship where we can trust each other, and I am able to delegate some things, some tasks to them, because I cannot do everything. But I need to be able to delegate without losing control of what's happening. So I need a very good relationship with these persons, which are great, by the way. I also need to find a good balance between having in mind the big picture, so the whole system, what's happening with it, and also to know which are the important details to follow. I cannot follow all the details, but I need to be able to understand which details are important and they can create problems in the future, so I need to keep an eye on them. And also another challenge lately has been, well, it's not, I wrote Zoom, it's not Zoom, it's a different tool, but it's the online meetings. It's very difficult to work with people that you have never met, only online. Sometimes you can't even see their face. You can't see their reaction to what you are saying. It's more difficult to establish a relationship. It's quite challenges. So thanks COVID, hopefully this is not going to last much more. Let's see, let's cross our fingers. So this was a bit a description of my job. Of course, I didn't have much time. I hope it's clear enough. Ask me a question if there is something that you don't understand. But before I finish, I wanted to also mention a little bit what it means to be an expat and to work and to live in a place that is not your home country. So this is me when I came to Holland 11 years ago. Here I am visiting a very nice flower exposition here in the Netherlands, the Keukenhof. It's really nice. This is Leiden, which is the city where I started living. Now I have moved. And this is my first house, and this is the first week when I came to the Netherlands. As you can see, I bought at IKEA a table, a bed, and a lock, and that was all that I had in the house. So this is just to say that moving to a different country is wonderful, and it's still, I think, is the best choice that I ever did, but it also requires a lot of work, a lot of adapting yourself to a new situation, and it can be also a little bit lonely, especially at the beginning. So you need to work to recreate a network of contacts and friends and people that can help you and that can keep you company. I think something that you had already maybe in your home place, but it needs to be done again. So it's a bit of work. Also, I recommend very much to learn the local language, even though, for example, here everyone speaks English, but it's really different. It really makes the difference if you put in the effort and learn the language. I did a bit, not as well as I would like, because at some point it can happen, for example, that a baby appears. In my case too, I have two kids. This is Bianca, and I have also Luca, who is now 3 years old. Here I wanted just to briefly mention that also having kids when you live in a different country is also a bit of a challenge, because maybe the medical procedures are not the same as in your place. Maybe you are far away from your family in the moment where you would need them most. And then, of course, also the practical organization, like, for example, when the kids are sick, you generally don't have your parents or your in-laws that can help you, or when a pandemic explodes and you can't send them to school, you don't have parents to help you with looking after them. Still, this is not to scare you. It's wonderful, and I still am super happy that I am raising my kids here. But also, I think it needs to be said that you need to be aware of what's ahead of you so that you are prepared and you are organized for these challenges. And then this last picture is me when we launched Solar Orbiter. I was in Germany, in Izok, which is where we have the ground station, so where we receive where we communicate with the spacecraft. And I was part of the payload support team, so I was in a team where we received all the data from the spacecraft, and we helped figure out if there was an anomaly, why there was an anomaly, what we could do to solve it. And we worked in shifts. We worked also for a few days during the night, and it was the best experience. It was really the most wonderful experiences of my life. And with this, I would like to encourage you to try to get out of your comfort zone and to be open to the opportunities of life, because really, as Elisabetta very well said, one step after the other, you can get here, you can get in very many places, and also you can have a lot of fun while doing that. And with this, I thank you. I stop my presentation. I think that now you can probably see me again. if you have questions, and anyway, I have also left my email address on the first page of the presentation. So don't worry, don't be afraid. Write to me if you want.
Okay, thank you so much, Lydia. I have to apologize with the girls because I messed up with activating the chat, and while I thought it was activated, it was deactivated. So I promise you, Jimena, that Elisabetta was going to answer to your question later. But I think she had to go. But please do not worry that I will send her your question and you will get an answer for sure. The first question comes from Maria that I'm going to read it. I have a question about the space station and about your work. If someone has a mental illness like anxiety, they have an attack, are people prepared to be able to calm and relax the person?
So, Maria, I am not really working on the space station, so I don't know a lot about it. What I do know, however, is that the astronauts that go on the space station, they go through a very thorough process of selection, and also they have a very, very thorough training. So I suppose that it's not so possible that something like that happens to them, or that they are anyway trained to control their anxiety. I think that a big part of their training is to control the emotion and be able to act rationally even when you are in very stressful situation. I talked at some point to an astronaut that said we do training, so we do, like, in the training we do the situations that we could face during when we are on the space station, and you have to do the training like it was in real life, and then when it happens in real life you have to do it like if it was in the training, so staying very calm and solving it. So I hope that this answered your question.
Mecia wants to know, what do you need to study to work in ESA, I suppose, because she just said
To
like
do that.
to do that, but well, I can do many things, Mencia, please.
So to work in ESA, you can study many things. You can study aerospace engineering or electronics engineering, like I did, or mechanical engineering as well. Some colleagues of mine are physicists, for example. There are many possible paths. For example, a dear friend of mine who does the scheduling, so the planning part, I think she studied philosophy. So there are many ways to get there. Of course, engineering is generally the easiest, let's say.
Okay, girls, I know that you all are tired because it's been a long session, and thank you so much, Lydia, for being here for all along
Of
this
course.
evening, and thank you so much. I just want to thank you, Lydia, because you've been the last one, but thank you to you, to Elisabetta, and also to Anne, because it's been great. And well, all the girls are just saying just the same. I think you can read the messages in the chat. So I think you've made very happy to quite a few girls, at least this evening. So thank you so much. Well, thanks for your
Thank you.
time.
Thank you. I hope to hear from you.
Yeah, of course. Have a good evening. Bye.
Good evening. Bye-bye.
Bye-bye.